Let's take a look at the construction of an AC motor to better understand how it works. The two major parts of an AC motor are the stator windings and the rotor. The function of the stator is to create a rotating electromagnetic field when alternating current is applied to its windings. To see how this is accomplished, let's take a closer look at the stator's construction. The stator of an AC motor consists of a hollow cylinder with electromagnets forming the walls of the cylinder. These electromagnets remain stationary. The rotating field that they form when current is applied is referred to as the stator field. An illustration of how 6 electromagnets are wired and oriented to create the stator of a 2-pole AC motor is shown in this wiring diagram. We can see that 2 electromagnets have been wired in series for each of the 3 phases. This is called a 2-pole motor because there are 2 electromagnets which contribute 2 electromagnetic poles per phase to the stator field. The electromagnets are positioned such that the resulting fields are 120 electrical degrees apart. The electromagnets in each phase of this 2-pole motor are wired such that when current flows through one pole or electromagnet, it flows in the opposite direction through the second electromagnet or pole. For each phase, the resulting magnetic fields, and hence poles, facing the center of the motor are reversed as illustrated. We have labeled the electromagnets or poles in each phase as shown. To understand how the rotating magnetic field is formed, we will create a convention. When an alternating sinusoidal current is applied to any of the 3 phases of the motor's stator, if the current is positive, that is, the current is above the x-axis, the A1, B1, or C1 electromagnets will be said to have been connected and oriented such that the north pole is located on the electromagnet's pole facing the center of the motor, while the A2, B2, and C2 will have the opposite, or south pole, facing the center of the motor. It is easier to visualize the resultant magnetic field if times are chosen when no current is flowing in one phase. This occurs every 60 degrees. Let's choose a start time when there is no current in phase A. At this time, phase B has current flow in the negative direction, and phase C has current flow in the positive direction. According to our convention, C1 and B2 are north poles, while C2 and B1 are south poles. The magnetic line of flux will leave at the north pole of C1 and enter at the nearest south pole B1. Magnetic lines of flux will also leave B2 and enter the nearest south pole at C2. The resultant vector shown is the vector sum of the magnetic fields formed between the C and B poles. If we repeat this evaluation 60 degrees later, phase C will have 0 current flow. Phase B has current flow in the negative direction, and phase A has current flow in the positive direction. With reference to our convention, A1 and B2 will be north poles, while will leave at the north pole of A1 and enter the nearest south pole at B1, and magnetic lines of flux will also leave B2 and enter the nearest south pole at A2. The resultant vector sum of the magnetic fields is shown here. If we compare the angular displacement of the field, we can see that it has rotated 60 degrees. If this evaluation is repeated every 60 degrees for the rest of phase A's cycle, we will see that the resultant stator field goes through one complete revolution, or 360 degrees. With a frequency of 60 Hz, this means in 1 second the field will go through 60 complete rotations, and in 1 minute 3,600 rotations. The speed of the rotating magnetic field is referred to as the synchronous speed. The synchronous speed can be calculated by the formula synchronous speed equals 120 times the applied frequency divided by the number of poles. If we apply this equation to a 4-pole motor, the synchronous speed is 1800 RPM.